This meeting is being recorded.
In the first section of Chapter 10, we're going to discuss radical reactions, and specifically in Section 1, we will be introduced to what a radical is, and then we'll continue with the remainder of these sections until we get to these reactions. I'm going to review of all the reaction types that we will see with radicals. So let's get started here with Section 1 in an introduction to free radicals. So when we have something called homolytic bond cleavage, where the bond breaks evenly, we will see radical formation. So that's what we see here. We have this compound that has 2 electrons shared in a covalent bond, and then with homolytic bond cleavage, each one of the atoms X and Y will receive one of those 2 electrons. So each X and Y in these green boxes here will have that single unpaired electron. So we indicate this, we indicate movement of electrons rather, previously in reaction mechanisms using a double barbed arrow or a full-headed arrow, and that's showing 2 electrons moving. But when we talk about radical reactions and movement of single electrons, we're going to use a single barbed arrow, or what's commonly referred to as a fishhook arrow. So you can see that the head of the arrow only spikes out on one side. So again, this is 1 electron moving. So in this covalent bond between X and Y, that's what we see. Those red arrows with a fishhook at the top showing only 1 electron moving. So what else should we know about radicals? We've seen a molecular geometry for carbocations, which would have a positive charge on a carbon. They have empty p orbitals, and they are trigonal planar because they have this sp2 hybridization of their orbitals. When we have carbanions, we have a filled sp3 hybridized orbital, right? They have a different hybridization, they're sp3, but with that lone pair, they end up with a trigonal pyramidal molecular geometry instead of a trigonal planar. But what happens when we have only 1 electron in this p orbital, right? Will it affect it? Will it make it more like trigonal pyramidal? Actually, what we see is something kind of in between and more like a trigonal planar type of structure. So that's what we're seeing over here. This p orbital in the red lobe, the top lobe, has that single electron there. And experimentally, we actually see that it's a very shallow trigonal pyramidal sp3 hybridization that results, almost appearing trigonal planar. So a radical reacts more like a carbocation than it does a carbanion when it comes to the molecular geometry involved with the reaction. So let's look at stability of radicals. They follow the same trend, so the same stability trend as carbocations, being that the least stable, just like with a carbocation, would be a methyl, right? So if we had a methyl carbocation, that's the least stable, just like a methyl radical. And all the way through, going primary, secondary, up to tertiary, we see that increase in stability with tertiary radicals, just like we saw with tertiary carbocations. So how can this be explained? We can explain this through bond dissociation energy, how much energy needs to be put in to break a bond. So that's measured here. We see with our methyl species here, our CH4, this CH bond indicated in green, that would require 435 kilojoules per mole to remove that, to break that CH bond and produce a radical. Until we get up to our tertiary over here, this would be the most stable, and therefore that would require the least amount of energy. So we see a weaker bond with a decrease in bond dissociation energy, and then our most stable tertiary radical would therefore require that least amount of energy to break that bond. So those two facts go hand in hand. The amount of energy to break the bond, the CH bond, to form a radical, and then the radical's stability. So just like delocalization through resonance of carbocations, we see this stabilization of that single electron through resonance as well. So let's take a look at this allylic radical species here. So the allylic position, if you recall, is this single bond next to a double bond. And this site right here on the end is what we refer to as that allylic position. So when we place an electron there, this becomes an allylic radical. So the movement, the fishhook arrows that are used to move this electron to show the resonance form are shown here. So we see these three red arrows, and that single electron moves in over here to form a double bond, and then one of the electrons from the existing double bond also moves in, and that's where we see the double bond movement over here from the radical electron and then from one of the pi electrons in the double bond. And then the other pi electron we see moves down here, so therefore our radical site has moved. So these are the two resonance structures for this allylic radical. So let me erase all those arrows so you can see the structure again, and those three curved arrows, those three fishhook arrows rather, that we use to show this electron movement. So we can also see radical stabilization with benzylic radicals. So again, this site here on the end coming out of our benzene ring is our benzylic site. So if you look closely, let me remove that circle. Where that circle was, you should see that black dot there. So we move that with a fishhook, and eventually this double bond's created when one of the other electrons over here from this double bond are moved in. So we have that new double bond formation, and then that other electron would end up top here. And then we see another set of three arrows, three fishhook arrows that move those three electrons around, and then we end up with this middle structure, and then we can do that two more times until we end up with a total of 5 resonance structures shown here. So a lot of times you're going to see a total of 5, 7, 12 possible resonance structures. The more benzylic sites, the more allylic sites, the more pi bonds that you have in order to accept electrons and relocate electrons. So this has 5 resonance structures, and because of that, benzylic radicals are more stable than those allylic radicals because they had less resonance structures. So let's take a look at this next slide here, and we can see that that trend of decreasing bond dissociation energy that we saw with our primary methyl, primary, secondary, then tertiary radicals. So we begin now with that tertiary radical here, and we can see that allylic radicals require less energy, so therefore to break the CH bond, to form allylic radicals rather, so that amount of less energy, that decrease in energy goes along as these radicals become more and more stable. And then we see the least amount of energy here with a benzylic site, so the radical site would be created on that carbon there at the benzylic site when that CH bond is broken. So that requires the least amount of energy, again, showing that trend of stability. So one last slide here with respect to radical stability. We've heard about vinyl sites. So that would be on the end of our double bond here, that the carbon on the end has those 2 hydrogens, and either of those could create, if we had enough energy, could create a vinyl radical at this vinylic site here. But you see that it has the highest amount of energy overall, 464 kilojoules per mole, compared to our allylic radical, which is about 100 kilojoules per mole less, to remove this proton here, or remove at least one of those electrons with it, and create that radical site. So if we were to identify the weakest CH bonds in a compound, we would use this trend as well. So that's everything from section 1. We'll continue with section 2 in the next video.